Okay, today I will do a quick example of Chaudhry Example 14.1. So this is an unsteady open channel flow problem that I will do in HEC RAS. And for the sake of time, I will not read all of the problem statement. But basically, we have a trapezoidal channel that on the upstream is connected to a reservoir, and that on the downstream has a sluice gate, like this. So in HEC RAS, you are able to include a sluice gate as an inline structure. And I looked at how to do that, but it will take a lot of time, and I actually don't really know how to do it. So we're going to do kind of a modification, but it still properly models what's happening in trapezoidal channel. Basically, we can show that the flow is being cut off and ending, but without having to insert an inline structure as a sluice gate, because I actually don't know how to do that, unfortunately. So I've taken all of the information that's given, and I've made my cross section. So these are all given, and I have just guessed the depth of the channel. I've said we should make the channel 10 meters deep. Actually, what I have done is I have used this open channel flow calculator to find the normal depth. So you can access this website, it's for free. If you Google open channel flow calculator Auburn, it should come up. It's from Auburn University. And you just select your channel type. You select here what you're wanting to solve for. It says select parameter for solving. And so I just clicked depth from Q, and make sure to set your unit system. And then I put in all of these given values. So I put in channel slope, I put in bottom width, left slope, right slope, Q flow discharge, and your Manning's N value. And then I clicked calculate, and it calculated this water depth right here to be 5.77. But since we're doing an abrupt closure of a gate, I thought, just to be safe, let's make the channel 10 meters deep. So all of these the cross-section data is made from these initial given data. And I have just set my datum to be 120. I don't know why that's right. So I've made my cross-section data for my most upstream reach and for my most downstream reach. Again, this is the problem statement, that we have a constant level reservoir and we have a sluice gate 5 kilometers away. And from the sluice gate point, we're going to cut off the flow and stop the flow completely. So first, in HEC RAS, we need to make a new project. And so I've started my new project already. And then from here, we go into view, edit, geometric data. To make a new project, you just file new project. But we'll go into making our geometric data. So I'll start by making the river reach. And you just click once and then double click. And we'll just call this river channel. And this is reach 1. So now we need to make cross sections. So first you have to click add new cross section. And I'll start with the most upstream cross section. And HEC RAS wants the most upstream cross section to have the largest number. So I'm going to say 5,000. and that will be my most upstream cross section. So I'll say it's at the reservoir. Okay. And now I'm just going to copy these values. And I'm going to paste them here. And since this is the most upstream cross section, and right now we're just going to enter 2 cross sections, it's asking for how long the reach is downstream from this cross section. So since this is the top, the most upstream, and our full reach is 5,000 meters, I'm just going to say beyond this reach, after this reach, we have 5,000 meters. And Manning's N is given as 0.013. Main channel bank stations, it means these stations here, what are the bounds of the channel? And so we're just going to say 0 for the left bank and 36.1 for the right bank, like this one. And then we can click apply. And that's our cross section. Since we've made it 10 meters deep and it's only 6.1 meters wide, that's why it looks the way that it does. So now we'll copy our current cross section to make our most downstream station at station 0. So I'll say this is the most downstream cross section at the sluice gate. So we copy our cross section data, paste it in. And since this is the most downstream, after this cross section, there isn't anything, we're done. So I'm just going to put 0 here actually, but all of the rest, the Manning N value is the same. And so we can just click apply. And now we'll exit and we will save our geometry data. And so now it shows we have 5,000 and 0 as our 2 stations. But I've decided, and the question asks for information in between 5,000 and 0. So we're actually going to subdivide or interpolate our cross sections. So if you go to Tools, XS interpolation or cross section interpolation, and we're going to do the interpolation within the reach. So we have our channel, our reach, and we need to select what river station is most upstream. So it's 5,000 is most upstream, and then it automatically selects 0 as most downstream. This is just asking the maximum distance between the cross sections. So I decided I wanted 50 intervals or 50 cross sections. And so each cross section will have 100 meters in between the cross sections. So I'm just going to say every 100 meters, make a cross section. And then we click interpolate. And we have all of our cross sections. And so I'll save it again. And you can see if we zoom in, that there is a cross section every 100 meters. Okay, so just save again, why not? And then I'll exit the geometry editor. Okay, so now we need to enter our flow data. So for the flow data, what's happening is we have Q is equal to 126 Qmax. And then suddenly the sluice gate closes and Q is equal to 0. So This change is occurring from downstream from the sluice gate. So in this column, I've made basically a hydrograph for the sluice gate that is acting from the downstream end. Remember, the sluice gate is down here downstream. So we're making a hydrograph for this location. And we are saying that at 0 seconds, discharge is 126 cumex. And then at the next second, it goes immediately to 0. So that's this hydrograph is being applied right here downstream. And we also will need to give a boundary condition for the upstream, which I'll show you in a little bit. First, we'll do this downstream boundary condition. Wow, that's so small. Okay, so we will need to go into our unsteady flow editor. So we'll click here and it brings up both of our boundaries. It has this upstream boundary condition at 5,000. And then our downstream, which is at 0, and it's our sluice gate right over here that I mentioned earlier. So first we'll just do this downstream. Basically, because we have flow in cumex, we'll say it's a flow hydrograph. So I'll click flow hydrograph, and we need to set our data time interval. So this is the time in your hydrograph. You see here it says hours, and then it runs by every hour. But I've made my hydrograph in 5-second intervals. So I'll actually change this to 5 seconds. And then you see here now it's 5, 10, 15, just like I've made over here. And then I'll just copy all of this and paste it in here. So 126, and then it goes all the way down. And so there's one more thing that we'll need. Right now, it's not clear that you need this, but if you run the model without inserting an initial stage, you'll get an error message. So we'll also need to put an initial stage. Maybe I'll run the model, and I'll just put it in now. So this is asking at this particular cross-section, which is our downstream cross-section, initially, what is the water stage level? What is the elevation of the water surface? So I've calculated over here that our normal depth is 5.77 meters. I just did that from this website. I didn't want to calculate it myself. And then I just added the normal depth from the elevation that I set over here. So for downstream, where the sluice gate is located, it's 109.6. So for the downstream, I just said it's the downstream 109.6 elevation that I calculated in the cross sections right here. Oops. It's just this elevation that I calculated for my most downstream cross section plus the normal depth. So just the bottom elevation plus normal depth. So that is my downstream water surface elevation. So I'm actually going to take this. Yeah, I'm going to take this number and I'm going to put it here because this is the initial stage. It's the initial elevation of the downstream water surface. Can I find, where's my hydrograph? Okay, so I'm just going to put in 15.37. And again, I'm using downstream because this is for the downstream hydrograph. So then I click OK. And then now we need for the upstream boundary condition. So upstream, we've been told that we have a constant level reservoir, that this elevation is always going to be what it is. So actually, we don't have enough information from the problem statement itself to know what this is, but in the solution, we can look at their graph and we can find out what it is. So we see at a distance of 0 kilometers from the reservoir, it's always at about 5.8. So I'm just going to say that the constant elevation is 5.8. So we'll take, that's the initial depth. So what I've done is I have just taken the upstream. Yeah, 5.77 is about 5.8. So this is fine too. I have just taken the bed elevation that I have made over here, 110, and I've just added the normal depth or added the initial depth of 5.8. And so I've made what's basically called a stage hydrograph. So this is again at the upstream location at the constant level reservoir. If you click stage hydrograph, you see that it gives stage in meters, which is basically depth, but it means elevation of the water surface. And so I'll change this time interval again to 5 seconds because that is the stage hydrograph I've made. And so again, I'll copy this water surface elevation and I'll put it in here. And again, it needs to be this elevation. If I just put 5.77, I would get errors. I already tried that and it doesn't work. So you do have to put the elevation. And that's all we need. And so we'll click OK. And then I'll go ahead and save this flow data. Chaudhry 14.1. Okay. And so now we'll make a plan. For unsteady flow data, and I'll just call it Chaudhry 14.1 plan. I'll just say when, it doesn't matter at this point what you put. Oh no, come back. Okay, and so you want these 3 boxes to be checked: geometry, preprocessor, unsteady flow simulation, and post-processor. And so we can just randomly pick a starting date. But since our simulation is only taking, what did I say? I'm going to run the simulation for 2 hours. So it's the same day. And since it's 2 hours, I'll just put the starting time as this is 0 to 2 hours. Yeah. So this means 2 hours, or this is like if you're starting at midnight and then running until 2 a.m. So because I've set my hydrographs in 5-second intervals, I'm just going to put this also for computation in 5-second intervals. And then why not? I'll also put these in 5-second intervals. You don't have to, but it won't take that long to compute. And so then I'll save the plan, and now I'll run the plan. Okay, great. So this is going to work basically just like we had put an inline structure at the downstream end. And so we'll be able to see in the results what it looks like. So this is our profile plot. We can look at it over time. So we can see this unsteadiness and this wave. So from the gate closing, it's causing this wave to oscillate back and forth. This is the benefit of running the model for 2 hours, that we can see this wave is continuing after 2 hours. We still have the wave going. So this is at 2 hours. So if you want to try to figure out how to do an inline structure, you would do that from the geometry editor. Under inline structure, there's an option to add a gate. Like we would need to add a sluice gate, and you can do that here. But there's a lot of settings, and I'm not quite sure how to do all of the settings and how to make it work properly. But for this example, actually, as you can see, we can do everything just as we need to, and perform the analysis without putting the gate in. So it's a little bit of a shortcut, but it still works.